Okay, so suppose on the test you're given a whole list of series like this, and you're asked to determine whether they converge or diverge. The first step to doing that is to figure out which test to use. So let's review that. Your first step is to see, do you have a recognizable form, either a geometric series or a p-series? If you don't have one of those, then you're going to want to apply the divergence test. So you'll take the limit as n goes to infinity. If it's not equal to 0, then you're done because your series diverges. If it is equal to 0, then you need to do some more work. So do you have a series with positive terms or alternating terms? For positive terms, we have the integral test, the direct comparison test, and the limit comparison test. And for alternating terms, we've learned the alternating series test, and now we're going to add the ratio test. So the ratio test is really great if you have factorials, which you all have had some practice on that worksheet. So that's why we were practicing those factorials. And also if you have something like n to the n, which is a hybrid of a p-series and a geometric series where both the base and the exponent are an n. So if you have a series that has those type of components in it, then the ratio test is a good choice. So let's look at the details for the ratio test. All right. So your ratio test, what you're going to do is you're going to take whatever formula you were given for your series, and you're going to find the ace of n plus 1. So what you'll do is you'll replace all of the n's with n plus 1, and then you'll divide that by ace of n, so what the original formula is. You'll take the absolute value of that, and then you'll take the limit as n goes to infinity. Okay, so let's look at the criteria for the convergence, divergence, and there's also a third category here for inconclusive. So it turns out that if L is less than 1, then our series is going to converge. And not only converge, but it's going to converge absolutely, since we have these absolute value bars here. If L is greater than 1, then it's going to diverge. And then if L is equal to 1, it's inconclusive, which means that you need to do a different test. Okay, it's kind of like a go fish condition. All right, so let's look at number 13. We'll give this a try. So number 13 is this series from n equals 1 to infinity of 2 to the n over n factorial. So let's start out by writing our limit. So L is the limit as n goes to infinity. The absolute value. Now I need the n plus 1 term. So that's going to be 2 to the n plus 1 over n plus 1 factorial. So I've taken my formula here and I've replaced all of the n's with n plus 1. And I'm going to divide that by 2 to the n over n factorial, the absolute value bars. Okay, so let's simplify that out. So this is the limit as n goes to infinity. Typically what I do, since I'm dividing two fractions, normally I skip this step altogether and I write this as 2 to the n plus 1 over n plus 1 factorial, and then times the reciprocal. So I'm going to flip the original term over. So that means this 2 to the n that was in the numerator is now in the denominator, and this n factorial that was in the denominator is now in the numerator. Okay, so I usually don't write this step. I usually skip straight to this. And this is going to be equal to the limit as n goes to infinity, and I'm going to rearrange this. I have 2 to the n plus 1 over 2 to the n times n factorial over n plus 1 factorial. So that gives me the limit as n goes to infinity. So 2 to the n plus 1 over 2 to the n just leaves me with a 2. And now you're going to see where that worksheet practice came in handy. So I have n factorial over n plus 1 factorial. So n factorial, and then n plus 1 factorial is going to be n plus 1 times n factorial. So those n factorials cancel, and I'm left with an n plus 1 in the denominator. Okay, and this limit as n goes to infinity. This is basically 2 divided by the federal debt plus 1. So this is going to go to 0. So L is equal to 0. So my conclusion here is since L is equal to 0, which is less than 1, my series n equals 1 to infinity of 2 to the n over n factorial converges absolutely by the ratio test, by RAT. All right, so there is our conclusion for the first problem.